Hey everyone. So today is our second lesson in trig. And really I'm thinking today will feel mostly like review. We're going to review how to get trigonometric angles or how to use trigonometric ratios and angles within all four quadrants using angles in standard position. And that was covered in 20-1. And then essentially in the next lessons where we'll get into some newer stuff when we deal with the unit circle. The unit circle is just kind of a small extension of what we do today. So once you get today down, I'll have to do a couple things with you in the next lesson, and then you'll be set for the unit circle, okay? Okay, so given that triangle ABC is a right triangle, determine the primary trigonometric ratios. Now, the primary trigonometric ratios were introduced to you in grade 10. They are the sine ratio, the cosine ratio, and the tangent ratio, okay? Remember that we always have to be dealing with an angle. So for this guy, theta is where I've stuck theta on A. So we're saying that that's the angle I'm looking at right now. So we would look at the sine of theta, the cos of theta, and the tan of theta, okay? Also remember that we do label the sides of a triangle with the same letters as their opposite angle. So opposite, remember, just means we're going from, like if this is A, have my pencil in that corner and I just draw away from it and it will always point to the opposite. So this is A, this is B, and this is C over here because it's opposite of C, okay? So the sine of theta would be opposite over hypotenuse, or in this example, it'd be A over B. The cos of theta would be adjacent over hypotenuse and C over B. And the tan of theta would be opposite over adjacent, which would be A over C. I'm curious, I'd like you to write down the Pythagorean theorem right now with relation to this triangle. And I'm hoping you wrote down b squared equals a squared plus c squared. Be careful that you don't just say, oh, no, it's a squared plus b squared equals c squared, because that was always the thing your teacher said. It depends on what letters are where, right? In this case, b is the hypotenuse, and the Pythagorean theorem always states that it's the hypotenuse squared plus a squared, or equals a squared plus b squared, the square of the other two sides added together, okay? All right, so now we also want to introduce three more ratios to you. In grade 10, I did mention this to my 10C class, if you were with me at that point, but there's actually 6 different ratios that I can do with 3 sides. And what we're missing here is the flipped versions, right? So if I can have opposite over hypotenuse and call that sine, why can't I have hypotenuse over opposite? I can. I'm going to call that cosine, or cosecant, sorry. If I can have adjacent over hypotenuse, why can't I have hypotenuse over adjacent? I can, that's called secant. And then if I can have opposite over adjacent and call that tan, why can't I have adjacent over opposite? I can, that's called cotangent. So we have cosecant, which is abbreviated CSC. That's the flipped version of sine. Now, this fact that cosecant theta is 1 over sine of theta, that is on your formula sheet, okay? So that's not something you have to remember, but I wouldn't look at it as 1 over sine theta as much right now as just hypotenuse over opposite. 1 over sine theta just means take whatever that ratio was and flip it. So it's much easier to look at it as hypotenuse over opposite instead of opposite over hypotenuse. Okay, you'll deal with 1 over sine theta a little bit more when we get into trigonometric identities. But for now, it's easier just to talk about it as hypotenuse over opposite. Okay, then there's secant, which is the flipped version of cosine. Please take note here, because a lot of kids get this mixed up. The co does not go with the cos. So the cosecant goes with sine, not cosine, okay? The secant goes with cosine. So secant theta is 1 over cos of theta, and that would be the hypotenuse over adjacent. And then the cotangent of theta is 1 over tan of theta, and that would be the adjacent over the opposite. So the pink ones here are called the primary trigonometric ratios, and then the blue ones that I just wrote down are called the reciprocal trigonometric identities. Okay. All right, so given a point x comma y on the terminal arm of an angle theta drawn in standard position, we can determine the six ratios. Now, hopefully that sort of wording sounds familiar to you from 20-1. If it doesn't, you're going to do a lot of practice with this today. So make sure you get comfortable. But we're always talking about an angle in standard position. So in the last lesson, we dealt with angles in standard position means that their vertex is at 0, 0, and their initial arm is on the positive x-axis. So right here, and then their terminal arm comes out into one of the quadrants. So what we're saying is the point xy, some random point lies on this terminal arm, okay? Now, to get the six trigonometric ratios, all we do is we drop a perpendicular from that point, that x comma y. So if I was to drop a perpendicular here, and I know that right there is the point x comma y, then I know that the base of my triangle has to be x, and the height of my triangle has to be y, because that's the only way to get to the point xy, right? In order to get to that point xy, I go over x and up y, okay? I'm going to call the hypotenuse r, and so we'll label this x, y, and r. Now, some of you may be saying, why are you calling the hypotenuse r? And my first answer is just because it's my favorite letter. And my second answer is no, that's not true. There's a reason, but we'll talk about it tomorrow. Okay, so now if I want sine of theta will be y over r, it's opposite over hypotenuse. Okay, cos of theta will be adjacent over hypotenuse, so x over r. Tan of theta will be y over x, opposite over adjacent. And now we'll do the other three as well. So cosecant of theta would be r over y. Secant of theta, that's the flipped version of cos, so r over x. And then cotangent of theta would be x over y, the flipped version of tan. While we're here, throw the Pythagorean Theorem at me. You're going to be writing down r squared equals x squared plus y squared. Okay, awesome. All right, so now we're going to put an actual point there. Given that the point -3, 4 lies on the terminal arm of an angle theta drawn in standard position, determine the six trigonometric ratios. So same question as we just did, except now we have a point there instead of x and y. And we're in a different quadrant. I would want you to look at -3, 4 as quadrant 2. Now, if you know you're in quadrant 2, draw a nice big quadrant 2, okay? It doesn't have to be that the center of your diagram is always the origin. Give yourself space so that you can see what you're doing. So I have an angle in standard position, and I'm going to pass through the point -3, 4. Remember that the angle in standard position always starts at the positive x-axis and then rotates. So this, I talked in yesterday's lesson about how important it is to write that rotational arrow so that we know the direction you're going. That is theta right now, okay? From the initial arm to the terminal arm, that angle of rotation is what theta is right now. I know I passed through the point -3, 4, so I'm going to drop a perpendicular from that point. Then I know that this is -3, this is 4, and that's enough information to get my hypotenuse. Okay, what happens is we actually build the ratios based on the reference angle, not theta, because the reference angle is always going to be an acute triangle, and that allows us to use sine, cosine, and tangent. Using the negatives allows us to actually get the proper ratio for theta, okay? So we can do it all based on the reference angle. You're gonna use the Pythagorean Theorem though, and you're gonna tell me that the hypotenuse here is 5. Either you went -3 squared plus 4 squared and then square rooted it, or you just saw that as a Pythagorean triple. That might be cool too. Okay, so I've got sine of theta is 4 over 5, cos of theta is -3 over 5, adjacent over hypotenuse, tan of theta is -4 over 3. It doesn't matter where you put the negative, except that we try not to put negatives on denominators. That's why I just pulled it to the front. Cosecant of theta would be 5 over 4, secant of theta would be -5 over 3, and cotangent of theta is -3 over 4. Now, a question. Why are some of these ratios positive and others negative? Well, it has to do with who's negative and who's positive in the quadrant, right? Like in quadrant 2, all your x values are negative and all your y values are positive. In quadrant 3, all your x values are negative and your y values are negative. In quadrant 4, all your x values are positive and your y values are negative. And then back in quadrant 1, everything is positive. And so that creates a little rule here that tells us, remember in the last slide, we said sine of theta was y over x. Well, if y over r. So if y is positive, then the sine of theta will be positive. Cos of theta was x over r. So if x is positive, cos will be positive. R is always going to be positive. That's why I'm ignoring that, just in case you're sitting there wondering about that. So we have something called the cast rule. And the cast rule tells us which guy is positive in which quadrant. So starting in quadrant 1, A is for all ratios are positive. In quadrant 2, the S is for sine. But now you also know that if I flip something, I don't change the negativity when I do that. So for sine, that's also for cosecant as well. Okay, so sine and cosecant are the only ones positive in quadrant 2. Cotangent and tan and cosecant and, cotangent and tan and secant and cosine would all be negative in quadrant 2. Going down to quadrant 3, only tan and cotangent are positive. So that means sine, cosecant, secant, and cos would all be negative. And then in the last quadrant, only cos and secant are positive. So that would make cosecant and sine and cotangent and tan negative. Okay. All right. Determine theta to the nearest degree if tan of theta is negative root 3 over 5 for theta is between 0 and 180 degrees. Also state the value of cosecant of theta. So we're in quadrant 2. Just like in the last example, I'm going to draw my little angle in standard position, drop a perpendicular, label what I know. So if I drop a perpendicular, I know that my x value here, we're looking at tan. So tan is opposite over adjacent. So I know that here's my root 3 and here's my 5. Which one's negative? Well, based on the quadrant, it would have to be the 5 that's negative. Now I'm going to use the Pythagorean Theorem to get the r. So negative 5 squared is 25. Root 3 squared is 3. So I'm looking at the root of 28. 25 and 3. The root of 28 here, which would reduce, that's 4 times 7, so 2 root 7. So my r value here is 2 root 7. Okay. All right, so now I've been asked to get I've been asked to get theta. So whenever I'm looking for theta, I actually kind of go through the back door and I get theta's reference angle. Okay, the way I get theta's reference angle is I use my tan or my sine or my cosine with the ratio I see inside that triangle, but I ignore all negatives. Okay, if I ignore all negatives, essentially I'm tricking my calculator into thinking I'm quadrant 1 and it will give me a 90-degree answer, like a acute answer, less than 90-degree answer. That will always give me the reference angle, and then I can figure out what theta is based on what the reference angle is. Okay, so always ignore the negatives when you're trying to find that angle, and then you'll always get the reference angle. So what I'm going to do is I'm going to say, okay, tan of theta's reference angle. Notice I put a little subscript r there just in my communication. I want to be really clear. I'm not actually solving for theta yet. I'm getting theta's reference angle. And theta's reference angle would be root 3 over 5. Theta's ratio. I'm going to just say that one more time. The ratio for tan of theta, that's better. Whoa. Okay. The ratio for tan of theta would be root 3 over 5. So if I know the ratio, I want to inverse tan or arc tan, root 3 over 5, and that's going to give me the angle. So when I do that, I get a reference angle of 19 degrees. Okay, I need to be in degree mode right now because I was dealing with degree measures, right? It said theta had to be 0 to 180. So make sure your calculator's in degree mode, and then you're going inverse tan or arc tan, shift tan. It's your second function of tan, however you get there. Don't ever call it shift tan though. call it inverse tan or arctan, of root 3 over 5, and then you get your 19 degrees. Now, theta, if 19 degrees is right here, theta would be 180 minus the reference angle. And so theta would be 161 degrees. Okay. You were also asked to get cosecant. So cosecant is the flipped version of sine. So if sine is the root of 3 over 2 root 7, cosecant will be the flipped version of that. So 2 root 7 over root 3. Okay, now in 20-1, it was drilled into your head that you can never have a radical on the denominator, and so you'd have to rationalize that. So to rationalize this, you'd go multiply this by root 3 over root 3, and you'd get 2 root 21 over 3. Now, quick 30-1 conversation. You don't actually have to do that in 30-1 unless you're specifically told to rationalize it. Okay, in 30-1, this is considered perfectly acceptable as long as the question didn't say have your answer in rationalized form. Okay, now I'm not saying that to stress you. I'm saying that to say this could appear on your diploma, this could appear on your diploma, and you need to be okay that both of them mean the same thing. It's just one is a rationalized version and one is a non-rationalized version. Okay, so don't let that stress you. Okay, so your calculator finds the angle differently than we will. The simplest thing to do is to drop the negative sign from our ratio. This will always give us our reference angle, and then we can determine theta. Okay. Awesome possum. Okay, let's try again. Given that sine of theta is negative 4 over 5, and theta is between 0 and 360, determine theta. Round your answer to the nearest degree. So I'm told that sine of theta is negative, and I'm allowed to go in all 4 quadrants because I'm 0 to 360. There are actually 2 quadrants where sine is negative. The ratios for sine are negative. So think back to the CAS rule. There are 2 spots where sine is not positive, if you want to think about it like that, and that would be quadrant 3 and 4. So I actually have 2 different answers here in quadrants 3 and in quadrant 4. So what I'm going to do, I'm going to find the reference angle, and the reference angle will be the inverse sine of 4 over 5. Remember, I'm going to ignore that negative sign. So the inverse sine or the arc sine of 4 over 5 will give me the reference angle, and then I'm going to use that reference angle in quadrant 3 to get an angle, and then use it in quadrant 4 to get an angle. Okay, so sine of theta's reference angle will be 4 over 5. So theta's reference angle will be negative, or sine to the negative 1. So arc sine of 4 over 5. And that's going to give me 53 degrees. So if I'm in quadrant 3, theta, if 53 is the reference angle, which I'm circling right there, theta will be 180 plus 53. And then in quadrant 2, theta will be 360 minus the reference angle. Okay, so we end up with 233 degrees and 307 degrees as my 2 solutions. Okay, and then you could always check, right? You could always go sine of 233 and see if you get a number that's close to negative 4 over 5. It's not going to be exact. 4 over 5 is 0.8. You're not going to get exactly 0.8, negative 0.8 there, because you rounded, right? That 53 was not an exact answer. It was a rounded value, but you'll get close. Okay, given that tan of theta is 5 over 12, and theta is now between pi and 2 pi. So I've now moved you to talk about radians. It's the exact same conversation though. We're just going to talk in radians. Determine cosecant of theta and theta. Leave the ratio an exact value and round your answer to the nearest 100th, your angle to the nearest 100th. So again, I'm going to draw a picture. I'm between pi and 2 pi, which means I have access to quadrant 3 and 4 right now. And tan is positive. So between quadrants 3 and 4, tan is only positive in quadrant 3. So I'm going to draw my angle in quadrant 3. I've got a 5 and I've got a 12. If this is my reference angle, tan of theta is opposite over adjacent. So that means my opposite will be 5, my adjacent will be 12. But I need to think about the negativity in quadrant 3. In quadrant 3, both x and y are negative. This is a very common mistake kids make in quadrant 3. Okay, both x and y are negative, and that's going to change what my ratio for cosecant is in a minute, right? So I end up with -5, -12. I use the Pythagorean theorem to get my hypotenuse, and that will be 13. The hypotenuse is never negative, it's always positive, okay? I think I've said that already, but I just want to make sure. Okay, so you were asked for cosecant of theta. Well, cosecant is the flipped version of sine. Sine of theta would be -5/13, so cosecant of theta is -13/5. I just flip it. Oh, sorry, I kind of did that a little too quick. Let me just go back for a sec. So -13/5 for cosecant theta. Is that okay? Yay. Okay, now I'm going to get the reference angle. So tan of theta's reference angle is 5/12. So I'm going to arctan it. So theta's reference angle is the arctan of 5/12. You have to make sure you're in radians right now because you were talked to in radians, right? It said between pi and 2 pi. It also said round your answer to the nearest 100. So that tells you you're dealing with some decimal approximation. It tells me you're not trying to deal with an exact value for your angle. Okay, so 0.3948 is the decimal version of theta's reference angle. So now to get the actual angle, remember that from here to here would be pi. So the actual angle will be pi plus my reference angle, right? Don't get confused because I switched to radians here. It's the same as saying my actual angle is going to be 180 plus 53 degrees, right? Which we did in a previous question. It's just that my 180 is now pi because I'm talking in radians instead of degrees, plus the reference angle, which is 0.3948. And so then now I don't round until I get to the final answer, and the final answer would be 3.54 radians. Okay, 3.54 radians. All right, good. So for the given point, sketch two coterminal angles in standard position whose terminal arm contains the point. Give one positive and one negative angle in radians where neither angle exceeds one full rotation. Round your answers to the nearest hundredth. Now this is a very wordy question, but it's actually not that complicated. Figure out where -2, -1 is. What quadrant would I be? I'd be in quadrant 3. And then essentially you get a drawing that looks like this. Well, now it says, give me two coterminal angles and neither one of them are allowed to be bigger than one full rotation. Well, okay, here's one. From there to there would be 1, right? And then the other guy would be this guy from there to there. Okay, neither of those are one full rotation. So that's what I'm going for. This is all that question's really asking, is get those two angles, okay? All right, so to do that, I'm still gonna drop my perpendicular and I'm going to label my sides. So I've got my x value is -2, my y value is -1. I need to use the, well, actually, no, I don't actually need the hypotenuse here. That's enough to actually figure this out, right? Because as long as I have one ratio, and right now I have the tan ratio, right? The tan of theta's reference angle here is 1/2. So I can just arctan 1/2. So the reference angle is 0.4636. I did that by making sure my calculator was in radian mode. And then I arctan, so second function tan, 1/2. That's where I'm getting the 0.4636. So that is the reference angle. The reference angle goes right there. Okay, so if I want two angles right now in standard position, well, the first guy, if I'm looking, let's just say I'm looking for this guy here, well, that would be theta plus my reference angle. Okay, so theta plus my reference angle. Whoops, sorry, I didn't realize my ink was still on. Theta plus my reference angle ends up being 3.61. So that's one of them. Okay. Now, to get the other guy, there's a couple different things I could do. I could look at this. If I'm going in this direction, I could say, okay, well, that's negative theta. So I could go negative theta plus my reference angle to get this piece, right? Because it was negative theta. If I add my reference angle, the magnitude will get smaller. The other way I could look at it is I could say, okay, I already know that this guy is from there to there is 3.61. So I could just subtract a full circle. And if I subtract a full circle, I'm back there, but what's left over would be that little piece that I was trying to find. Okay, either one will get you to the same answer. It doesn't matter. Okay, so I went negative theta plus 0.4636. So I did the first thing I suggested. And that gives me negative 2.68. Okay, but if you want to check, you could just go again. If you liked the other way better, go 3.61 and subtract a full circle. So subtract 2 pi. And then that would also give you negative 2.68. Okay. Okay, cool. So, oh, let me take that ink off for you. So here is your homework for this one. Like I said, make sure you draw these guys out. Make sure you're clear. Don't just draw your drawing little tiny thing. Make sure you can see and I can see what's going on in your drawing, okay? Give this a try, and if you have any questions, you know where to find me. In the meantime, have an awesome day. Take care, guys.